Okay, so hi everybody. So this is a talk about the paper Bit Complexity of Jordan Normal Form and Polynomial Spectral Factorization. And this is based on joint work with Papri, Ravi Kannan, and Nick Ryder. Here's an outline of the talk. So I'll start by telling you what polynomial spectral factorization is. And it's essentially a type of positivity circuit for matrix valued univariate polynomials. Then I'll tell you what Jordan normal form is. And it turns out this is the key ingredient to getting an efficient algorithm for polynomial spectral factorization. And then I'll tell you our algorithmic results for Jordan normal form and the key condition number estimate that goes into the proof. And finally, I'll end with some open questions about all of these things. There are lots of open questions. Okay, so let's begin by recalling a positivity certificate that we're all maybe familiar with. And that is for univariate polynomials. So suppose I have a monic, non-negative univariate polynomial of degree 2D over the reals. Then there's a certificate of this positivity. Namely, I can write P of x as q bar x times q of x for some complex polynomial q of degree D. And here bar is just a complex conjugate. So this is certainly positive because the right-hand side is a complex number times its conjugate. So this is a positivity certificate. And the proof of this is very simple. Well, if P is non-negative on the real axis, then all of its real roots have even degree. And so for each of those real roots, you put you just take one factor and put it in Q. And then the rest of the roots are complex and they come in conjugate pairs. And so we simply take Q of x to include all of the complex roots in the upper half plane, along with those, real roots that we chose in the first step. Okay. Another positivity certificate you might be familiar with is for matrices. So if you have a positive semi-definite matrix, n by n matrix, then it has a Cholesky factorization. So you can write it as Q star Q, where Q is a complex n by n matrix, and star is the adjoint. Actually, in this case, you can even take Q to be real. So it turns out there's a very nice generalization of these facts, common generalization, to the setting of matrix polynomials discovered by Rosenblatt and I don't remember who HL is in 1958. And this is called polynomial spectral factorization or matrix Fiery's factorization. So here's the statement. If you have a matrix polynomial P of x, so that's an n by n matrix whose entries are polynomials. And let's say it's degree 2D and it's monic. So the leading term, if you write it as a polynomial with matrix valued coefficients, is the identity. So let's say you have such a polynomial with real coefficients. And let's suppose you know that it's positive semi-definite for all x. So this polynomial, whenever you plug in a real x, is positive semi-definite. Then the conclusion is that you can Cholesky factorize this at the level of polynomials. Namely, there is some complex polynomial q of x, which is an n by n matrix polynomial of degree D, such that you can write P of x as q star x times q of x, where q star x means you take the adjoint of all the coefficients of that matrix polynomial. So this is now a positivity certificate because if you plug in a real x, the right-hand side is actually the Cholesky factorization of P. So this was originally discovered, and the motivation was related to control theory, and it has a lot of uses in dynamical systems. And the way we became interested in it is it's the key ingredient in one of the proofs of the Helton-Vinnikov theorem in geometry of polynomials. So the algorithmic question about this theorem is, well, if I give you a P of x, if I give you some integer P of x, can you compute this this Q of x? That's the positivity certificate. So that's the question that we're going to focus on for now, the algorithmic question. And let me briefly review what's known about this. So this has been studied quite a bit over the past few decades, and there are many constructive methods for finding this Q. So some important ones are There's a reduction to solving a semi-definite program. There's a reduction to computing the roots of a polynomial. There's a reduction to computing the Schur form of a matrix. And then there's a reduction to computing the Jordan normal form of a matrix. And that last one is due to Gochberg, Lancaster, and Rodman from 1980. So these are very nice results, but the downside is that they all require us to solve each of these problems exactly. For example, solving an SDP exactly or computing a Jordan normal form exactly. And none of these things can actually be done exactly on a computer in a finite number of bit operations. So actually, these results don't give a provable polynomial time algorithm for this problem. And so the first theorem of this work, called theorem A, is a polynomial time algorithm for this problem. So the theorem says there's an algorithm which does the following. So given a matrix polynomial P of x with dimension n by n and degree 2d, and real coefficients that are actually now integer with a bit entry. So I'm going to use this notation, bracket a at the end. I'm going to use this notation bracket parentheses a to denote that every entry of this matrix polynomial P of x, so every entry of every coefficient has a bits and is an integer. So suppose I'm given an a-bit integer matrix polynomial. Then the algorithm computes some matrix polynomial q prime of x, such that q prime is close to q, is used to the true q in the spectral factorization, up to some epsilon times the norm, where this norm is just the entry-wise maximum of all the coefficients that appear in the polynomial. So to either compute an approximation of the polynomial matrix, the polynomial spectral factorization, or certify that no such spectral factorization exists. So if you give it a polynomial that's not positive semi-definite on the real line, it will certify that. And the running time is polynomial in d, the dimension of the d, the degree, n, the dimension of the matrices, a, the number of bits in the matrices, and log 1 over epsilon. And so the running time is given here. So this is, it's not a very small running time. It's roughly d to the 6, n to the 6. But it's some concrete running time for this problem. So I won't tell you the full proof of this theorem. The analysis is basically it contains two components. One is a robust analysis of this reduction to Jordan normal form due to Gochberg, Lancaster, and Rodman. And the other component is an improved algorithm for Jordan normal form. So I'll spend the rest of the talk telling you what that improved algorithm is. And once we get that algorithm, that gives us theorem A. Okay, so what is Jordan normal form? So Jordan normal form is a normal form for square, let's say, complex matrices. And it's the following fact: if you have a square complex matrix, n by n, it's similar to a direct sum of Jordan blocks, where a Jordan block with eigenvalue lambda is a matrix that looks like this. It has lambdas on the diagonal and ones on the superdiagonal. So in particular, if you have a diagonalizable matrix, then in the Jordan normal form, all of the Jordan blocks are of size 1. And this is diagonalization is a special case of this. And the columns of the similarity V that appear in the Jordan normal form are generalized eigenvectors of the matrix A. So this appears in many, many settings. For example, in applied math, it's relevant in dynamical systems. In theoretical computer science, it shows up when you're trying to study the non-backtracking matrix, which is how I learned about it. And in algebra, it shows up in lots of different ways. For example, the Jordan-Chevalier decomposition of an algebra. So that's a Jordan normal form. And the algorithmic question we'll study is, given an integer n by n matrix A with little a bits per entry. So again, I'm using this notation with the bracket parentheses. So given an integer matrix and some desired accuracy epsilon, I would like to compute some j prime and v prime, which are close to a true Jordan normal form Vj of this matrix. So that's shown here, and let's say the norm is the operator norm. And this is the forward error formulation of the problem. It means given an input, I would like to compute something which is close to the exact output for that input. Some remarks on this problem. So you can't compute this exactly because, well, in particular, it involves computing the eigenvalues. One feature that makes it challenging is that the output is discontinuous in the input. So if you have a matrix with, let's say, if you have a matrix which has some Jordan blocks of size greater than 1, in general, if you perturb it even infinitesimally, you'll get something with a matrix that has different Jordan blocks. And this is not a solved problem even in practice. If you try to use standard computer algebra or just numerical packages to compute this, it's pretty slow even for a 100 by 100 matrix. So the goal now is to have a provable algorithm for approximately computing this Jordan normal form in the sense of forward error in polynomial number of bit operations. So what's known about this? So there are roughly 2 lines of work. So the first one is in the symbolic computation community. Some of the highlights are the work of Kaltofen et al. In 1986, Ozello in 1987, and culminating in this theorem of Geisbrecht in 1995. And what this line of work ultimately was able to prove is that given a matrix A, you can compute some kind of symbolic representation of the Jordan normal form. So you can compute V as an element of a certain field extension in the eigenvalues of the matrix using roughly n to the omega exact arithmetic operations. So I'm using this star to suppress logarithmic factors in n and a. You can compute this in roughly matrix multiplication time, but that's the number of exact arithmetic operations, and you must be given the exact eigenvalues in this. There's a model of computation where you can be given some complex numbers which are the exact eigenvalues. So this is very satisfying because that's a very good bound, but it doesn't give any bit complexity because we actually care about Boolean operations. So how many bits needed to store the numbers, etc. And of course, it assumes that you're given the exact eigenvalues. So nonetheless, there's an important, the ideas in this work are very important for what I'm going to say. This algorithm is based on a very nice idea, which is related to something called the Frobenius canonical form. So a key idea that appears in these proofs is that, I mean, it's a fact that every integer matrix is similar to a direct sum of companion matrices. That's called the Frobenius canonical form. So it's not the Jordan normal form, but it's some other kind of canonical form. And to remind you, what is a companion matrix? If I have a univariate polynomial of degree n, as shown here with coefficients ai, and let's say the leading coefficient is 1, then the companion matrix is an explicit matrix shown on the right here, whose characteristic polynomial is equal to that univariate polynomial. And the coefficients of the univariate polynomial appear as entries in the companion matrix. So the Frobenius canonical form is a statement that every integer matrix is similar to a direct sum of companion matrices. And the nice thing about this is you don't need to compute eigenvalues. This can be computed exactly without any error in polynomial time. Okay, so that's the symbolic computation community. In the theoretical computer science community, there's an important theorem. There's only one result about this. It's an important theorem of Psi from 1994. And what he showed is that given an A-bit integer n-by-n matrix, you can compute a forward approximation of the Jordan normal form in polynomial time. So the degree of the polynomial is not specified, but if you look at the proof, you can see that it's at least 12. So this is very good, but it doesn't give an explicit polynomial runtime. And in fact, it's interesting to see that An and Sai wrote a paper around the same time, published in Soda, where they proposed Jordan normal form as an uncheatable benchmark for proving that a computational device has a lot of power, so as a proof of work. So somehow this was actually being viewed as a very difficult computational problem, which it is actually at the time. Okay, so that's the prior work. And so the new theorem is theorem B, which is an explicit polynomial runtime bound for computing the Jordan normal form. And so it says, given an A-bit integer matrix, you can compute these V prime, J prime, and V prime inverse. So again, we also want the inverse we compute to approximate the true inverse in this many bit operations with forward error epsilon. So it's roughly n to the 6 bit operations for an n-by-n matrix. And there's this dependence on the number of bits of the matrix as well. So I won't tell you exactly what the algorithm is. It's not very complicated. it combines some results from the symbolic computation community with some numerical ideas. But I'll tell you what the key structural lemma in the proof is. And the key thing that needs to be proven is that if you have an integer matrix A, then there is always a Jordan normal form in which the similarity is well conditioned as a function of the number of bits of the input and the dimension n. So the statement is given any integer matrix n A with A-bit entries. There is a Jordan normal form where the condition number of this similarity V is bounded by exponential in an cubed. So, I mean, some such bound has to exist, right? The number of n by n matrices with A-bit entries is finite. And so there's some bound on this condition number, and this is saying that this is what this bound is. Oh yeah, and the condition number is a product of the norm of V times the norm of V inverse. So roughly speaking, the reason this is relevant is that if you have a matrix with a bounded condition number, then there are results saying that you can store and manipulate it using roughly log of that condition number bits of precision. In particular, there's a very nice result of Storjohann on inverting integer matrices or rational matrices of bounded condition number. And so once we have this condition number bound, these type of results tell us that we can manipulate these matrices in using an cubed bits of precision. And this n to the 6a roughly is n cubed times n to the 3a for inverting such matrices and so on. Okay, so let me now tell you the proof of this key condition number estimate. So this is the key lemma. Given an integer matrix A, there's a factorization. There's a Jordan normal form where the similarity has condition number at most exponentially n cubed. And this proof combines both symbolic and numerical techniques. It doesn't do anything that fantastically new. It just combines techniques from a bunch of different areas. Okay, so we have this matrix A, integer matrix, and we want to bound the condition number of this V. So the first step is to appeal to a result of Geisbrecht and Storjohann from 2002, which says that any integer matrix is similar to a companion matrix. This is the Frobenius canonical form I mentioned earlier, with some control on the number of bits in this Frobenius canonical form. Okay, so if A has little a bits, then it can be written as FCF inverse, where C is a companion matrix, F is invertible, and F has an squared bit entries, and C has an bit entries. So the added thing here is control on the entries, the bit length of the entries. And they prove this via a fairly complicated algorithm, actually. So that's the first step. So you write the Frobenius canonical form with controlled bit length. Okay, the second step is now to try to compute the Jordan normal form of the companion matrix. And this is something for which explicit formulas are known. So companion matrix is a very structured type of matrix. And there's a result of Brand from 1964, which says that if you have a companion matrix, its Jordan normal form is very explicit. In particular, the similarity is something called a confluent Vandermonde matrix in the roots of the companion matrix, so namely in the eigenvalues of the matrix. And this, I won't tell you exactly what a confluent Vandermonde matrix is. It's something like a Vandermonde matrix. The entries are explicit, nice polynomials. And so what this means is that I have some kind of very good structure for the Jordan normal form of the companion matrix. So now it would be nice if I could bound the condition number of this similarity U in the Jordan normal form of C, because then I could push that back to get some control on the similarity for the Jordan normal form of A. So how do I do that? Well, there's a result of Batenkov from 2012, which says that if you have a confluent Vandermonde matrix, as we do in this situation with the companion matrix, then the norm of its inverse, or actually even its condition number, is bounded by so the norm of its inverse is bounded by a function of the minimum eigenvalue gap of the matrix. So this is kind of interesting. It's saying that the condition number of the matrix of generalized eigenvectors, actually, the norm of the inverse can be bounded purely in terms of the gaps between the eigenvalues. So if this companion matrix has well-spaced eigenvalues, this similarity U will be well conditioned. So now this reduces our problem to bounding eigenvalue gaps of this companion matrix C that we obtained from A. And now we know that C has AN bits from the first result, right? And so that allows us to use a result of Mignotte from 1964, which says if you have any polynomial with integer entries, then the minimum gap between distinct roots of that polynomial is at least exponential in minus AN, where A is the number of bits of the coefficients of the polynomial. So how do we apply this in our setting? Well, our polynomial C is just a characteristic polynomial of the companion matrix. And the coefficients of that polynomial are just entries of the companion matrix. So they have bit length at most AN. And so applying this lemma, it means that the minimum gap between distinct roots of these companion matrices is at least exponential in minus AN squared. And now when we plug that into the condition number bound from step 3, when we plug this gap bound into the above, we get that the condition number of the similarity U in the Jordan normal form of C has condition number at most exponential AN cubed. And now finally, we just combine all these things. We use the fact that the norm of the inverse of an invertible matrix with A-bit entries is at most exponential AN, roughly. So I'm ignoring, I'm ignoring some lower order terms here. Yeah, there are constants and some log factors everywhere that I'm ignoring. So then that implies that, well, I know that the condition number of U is at most exponential AN cubed by this gap argument. I know that the condition number of F is at most exponential AN cubed because it's an AN squared bit invertible integer matrix. So if I combine both of these things, I get that the condition number of V is also at most exponential some constant times AN cubed. And that's the proof of the key lemma. And the interesting thing is you can't really do this if you use purely analytic techniques or purely symbolic techniques. You kind of need both. So that completes the proof of the key lemma, which then completes the proof of this theorem, which then is used to give the proof of this polynomial algorithm for computing the spectral factorization of a matrix polynomial. So that's it. Let me end with some open questions. So there are lots of open questions. So one is, I don't know if this n to the 6 is tight for Jordan normal form. It can be improved to n to the omega plus 3, but I don't know if that's tight. So one question is, what is actually the bit complexity of Jordan normal form? It's a very fundamental problem. It'd be nice to know what the right answer is. And that's a computational question. The key structural question that underlies this is this condition number bound. So I don't know if this exponential AN cubed is tight. And so the structural question is, given an integer matrix, how large can the condition number of the similarity be? Could it be improved to exponential AN squared? I know it cannot be improved beyond that. Another related family of questions is about diagonalization. So what is the bit complexity of diagonalizing a diagonalizable matrix, diagonalizable integer matrix? And this is not known. So we know that for backward error, which is the notion of error in scientific computing, it's nearly matrix multiplication time. But we don't know for forward error. And so you can ask this question both for general diagonalizable matrices or for symmetric diagonalizable matrices, the matrices that we see all the time. And we don't know what is the complexity of computing the eigenvalues and eigenvectors with forward error of a symmetric integer matrix. And again, the key structural question that underlies this is some kind of question about conditioning and eigenvalue gaps. So a very combinatorial question that would allow you to make progress on this question is, given a symmetric n by n integer matrix, how close can two of its distinct eigenvalues be? We don't know the answer to this. So the best lower bound is exponential in minus AN squared. The best upper bound is exponential in minus AN log n. And there's a huge gap between those. I should mention that the symmetric is very important. So recently in this work with Abrams, Landau, and Palmersheim, we showed that if you have a non-symmetric integer matrix, then indeed you can have two eigenvalues that are exponential minus AN squared close. And then finally, there's the question of improving the running time for spectral factorization itself. So we gave some algorithm that reduces it to Jordan normal form. That may not be the fastest algorithm. Maybe analysis of the semi-definite programming algorithm would give a better bound, etc. And then finally, can we get an algorithmic Helton-Vinnikov theorem in geometry of polynomials out of this? So yeah, that's it. Thank you.